I want to quickly go through those topics again so that you can have a more understanding on that. So I won't be discussing much on formulation, but I'll be talking more on what is plane stress, what is plane strain. Okay. So plane stress typically, like if you see, we can do modeling a problem as a plane stress. If it is having a one dimensions which is thin compared to other two dimensions, like thin plates. Okay, if you see here, for example, this is a hollow plate, very thin. Okay, so here we can model this as a area component. Okay, with hollow, with hole, and we can assign the thickness. So this is a plane stress problem. So I hope everybody is able to see my screen. If you have any issues, just you can mention in the chart. Okay. Similarly, this is a plate with hole. Okay. Here we can model only area with a hole, and we can assign the third dimension as a constant thickness to this complete area. Okay. So this is a plane stress thing. And one of the important thing is because it is very thin, it will have zero stresses. Okay, zero stresses across the thickness. So this is related to formation which we discussed. I don't want to spend time here. So it's a self-explanatory. If when you get this document, you can review, and if you have any questions, you can ask me. So coming to plane strain, this is contrast to the plane stress problem. Here, one of the important factor, one of the important assumption thing is like the third dimension is much larger, whereas in plane stress, the third dimension is very small. Here it is very large compared to other two dimensions. So here our model is, suppose this is example of dam subjected to water pressure. Okay, so here we model only this cross section. This area only will model, and we'll assign the thickness. This length as a constant thickness to all these elements. Okay. So similarly, pipe subjected to vertical pressure. Here also will model only this area, and we assign third dimension as the length of this pipe to the elements. So here the strains, because it is very large, the strains will be very small and negligible. In session, so I'm in session. Okay, I'll give. Can you send through mail? Yeah. Yeah. So the third dimension is very large. So we assume the strains will be negligible. That is the important assumption here. Similarly, this is the formulation, and coming to axisymmetric. So this is one of the important assumption in our stress analysis. Suppose like we in general we'll be having a lot of axisymmetric problems where we need to simplify into a 2D problem as an axisymmetric problem. For example, if you take this rotating this component, this is purely axisymmetric. If you take a cross section here, if you try to revolve about the axis, it will come as a cylindrical component. So some of the things is some of the important things about axisymmetric is no variation in circumferential direction. That means there won't be any changes in the geometry in circumferential direction. So if you take any section in the geometry, it should be remaining same, described by rotating a 2D cross section 360 degrees about axis. So, and the displacements will be constants in circumferential direction. So along the circumferential direction, the displacements will be constants, and loading and deformation are confined to radial and axial direction. So the loadings will we can apply only in axial direction or radial direction. Okay, we cannot apply any load in 360 degrees. So loading can be applied along axis, along radial direction, or along axis. Okay, you cannot apply. You cannot apply. Okay. So this in analyzing pressure vessels, pipes, shafts, and aero engine rotors. So this is the one of the important example. Like this is a turbine rotor, aero engine turbine rotor. Here we can model this complicated assembly into very simplified way. And this is the rotor, and this is the attachment where blade will be locked here, and blades are simulated using mass elements. So one mass element represents blade mass, another element represents gas loops. So these elements are tied to the blade attachment region. So here we have used two techniques. One is axisymmetric technique here, and we assigned plane stress with thickness because it is not a 360 degrees constant. There will be slots will be there, so that we model using plane stress with thickness. This is one of the example. And coming to axisymmetric formulation, general we will be having XYZ coordinates, but in axisymmetric we typically use R, theta, Z. Okay, where R represents the radius, Z represents axial, and theta represents hoop or circumferential. So in general, in axisymmetric problems, radial displacement develops circumferential strains. Um, it is if it is subjected to a load, definitely these cylinders will try to act, and the radius will change from R to delta R plus delta R. Okay, then if you try to measure the circumferential strain, that is circumference length is given by 2 pi r. Okay, and if you use the 2 pi r thing, you will get uh, strain as a ur by or delta r by r. Okay, so in axisymmetric problems, radial displacements always develop circumferential strain. Okay, so this is how it is explained here. Okay. So this is formulation of axisymmetric. Yeah. Now let us look into the chapters. So still we are into model idealization techniques. So we'll be discussing more on symmetry and cyclic symmetry. the things. Okay, where one of the advantage of symmetry conditions using symmetry conditions is we can reduce the degrees of freedom, or we can reduce the model size, problem size, which in turn decreases the computational time. So as I mentioned earlier, we can do symmetry. We can go for modelization symmetry if and only our more problem have a symmetry in geometry, material properties, and degrees of freedom constraints. If they have all these things have the symmetry, then only we can go for symmetry boundary conditions or symmetry simplifying the model. For example, take this geometry here. Okay, if you take this geometry, it is symmetry across this line, this dotted line. And coming to loads, okay, there are two load vectors here, this side, and there are two loads this side. Their loads are perfectly symmetric. Geometry is symmetry and loads are symmetry. And coming to displacement vectors, this model is exhibits complete perfect symmetry about this axis. So some of the things about symmetry, it is easy to create symmetric model. So no need to model complete assembly. We can take the symmetry and we can model it. Modeling is very easy. And one of the another advantage is you can use finer modeling details. For example, like if I take a so if I take a if I try to mesh this model with some elements, say 9 elements, and it is unsymmetry about this line. Okay. Same model if I take symmetry, off symmetry. So instead of 3 elements, I can put more elements. Okay. So this will have quicker convergence. So I have put more number of elements and I'll get a better accuracy in model. So I put more number of elements and at the same time it will have better convergence because I put more elements here and I can capture the geometry. Okay. Similarly, for more example, let us take another example. Okay. So if I try to mesh this geometry, it is very coarse mesh. Okay. So here getting convergence with this mesh is very tough. So what we can do is we can take this model and I can put more number of elements here. Okay. This will have more convergence compared to this one. So it will allow to put more number of elements, resulting into better convergence compared to the complete model. So there are various types of symmetry. That is axis symmetry that we discussed. Then rotational symmetry, also called as cyclic symmetry, planar or reflective symmetry, repetitive or translation symmetry. These are some of the types of symmetries: axis symmetry, rotation cyclic symmetry, planar or reflective symmetry, repetitive or translation symmetry. Let us look into one by one. So axis symmetry we already discussed. Coming slides won't discuss more on axis symmetry. We'll be talking about cyclic symmetry, planar symmetry, or translational symmetry. These three symmetries we'll be talking. Coming to cyclic symmetry, a structure possesses rotational symmetry when it is made up of repetitive segment arrangement about central axis. Okay. So when I try to, if you see this fan blade assembly, it consists of some number of blades. They are similar. All the blades are similar. Okay. There won't be any variation. So here, what we'll do, what we need to do is like we can model only this part, okay, and enforce the symmetry boundary conditions, cyclic symmetry boundary conditions. That makes it as a equivalent to the complete fan blade assembly. So here it will reduce enormous modeling efforts. Okay, instead of modeling complete 360 degrees with the complicated blade, we can model only one blade and do the analysis. And at the same time, we can concentrate on area of interest where we can put more number of elements. Like for example, at this location, fillet locations, some of the critical locations, we can put more number of elements. So whereas if you try to model complete 360 degrees, it will take enormous amount of computational time. It will take a lot of time in analysis. It will take more time in post processing. So this is how we can reduce the problem to cyclic symmetric problem. So loading is here. Loading is assumed to be symmetric about axis. So for this type of problem in fan blade assembly, typically there are some loads acting on the blades. So this is the rotor. This is blade. So blade is subjected to omega or angular velocity. Okay. So here it is. Okay. So it is angular velocity. This is uniform. Okay. Angular velocity, and it is subjected to pressure load. So pressure load coming from gas part. Pressure. This will calculate as a pressure load. So pressure load is uniform. Okay. It will this load will be acted on throughout the 360 degrees. So pressure load is also uniform. Similarly, there will be thermals varying from top to bottom. Okay. So that is also uniform throughout 360 degrees. So one of the important thing for cyclic symmetry or axis symmetry, load should be uniform. So we have three loads here. One is pressure load, temperature, and angular velocity. So all these three loads are symmetric about axis or symmetric throughout the 360 degrees or cyclic symmetry. For one, if you take one blade, so this blade loads acting on this blade will be repeating for all the blades. Now more on cyclic symmetry. Cyclic symmetry is described by two things. One is number of replication about axis. Another one is minimum sector angle. So if you take like if we have number of replications are 3, then the angle between the angle will be 120 degrees. That is 360 by then 3. It will give 120. So similarly, if we have number of replications 4, then the angle will be 90 degrees. Okay. Similarly, number of replications by the angle will be 70. So here, this problem, we can model only this part. This is sufficient. And for this problem, if you model this part is sufficient. For pentagon, if you can model this one, it is sufficient. And coming to cyclic symmetry again, if you have number of repetitive features 8, then the sector angle will be 45 degrees. Okay, so here what we can do is what we do how to model this number of repetitive features 8, right? So total angle, the sector angle will be 45. So now the important thing is how we'll take this sector angle. So here what we'll do is like we'll take this center line and we'll take either side, okay, and this part will model it as a single sector. So that was represented here. So coming to, there are two cut planes will be there, plane A and plane B in this model. So displacement set plane A will be equal to displacement set plane B. That was represented here. There was a typo here. Instead of A, it should be B here. So UAX, displacement along x direction at plane A equal to displacement along x direction at plane B. Okay. Similarly at y and at z. So this is the important condition for establishing cyclic symmetry. The reason why the displacement, the one important question will be there, like why the displacement should be equal, because our loadings on the each sector is similar. Okay, whatever load acting on this sector is same as load acting on this sector, similarly other sectors. Okay, so that means this complete 360 degrees model will deform uniformly, okay, along the axis, along the axis of rotation. That is the reason this condition will exist. So cyclic symmetry is found throughout air engines and steam turbines. Even like if you have any other rotating components, this cyclic symmetry usually exists. So in air engines or steam turbines, the cyclic symmetry exists in compressors, fans, turbines, and gears. So one of the typical example here, this is the 360 degrees model. Okay, if you model complete 360 degrees and do the analysis, and if you model only small model, one sector and do the analysis, the results will be same. Okay, only thing is we need to impose cyclic symmetric conditions at the cut sections as discussed here. So it is very important for us to establish this cyclic symmetric conditions at these cut sections. Then only model can be behaved similar to 360 degrees model. And that is about cyclic symmetry. Now coming on symmetry. So symmetry, there are two different things are there: symmetry and anti-symmetry loading conditions. In symmetry, a symmetry line in two dimension can be recognized by remembering mirror displacement pattern. Okay, so if you take this geometry, if you take this line, so this part is perfectly mirror symmetry of this part. So, and also alternatively, a 180 degrees rotation of the body about symmetry line produces exactly original problem. So if you try to rotate this component 180 degrees, okay, so 180 degrees in this direction about this line, okay, so it will exactly compensate at this location. So this is also defined as a symmetry. So here again, like what we discussed, symmetry means it should exhibit symmetry in terms of geometry, in terms of material properties, in terms of loads, in terms of displacements. So then only we call it as a symmetry. So geometry, material property is symmetry, but loads will be acting completely reverse. If you take this example, if this is the dotted center line of symmetry, when you try to rotate about this line, anti-symmetric line, so this geometry will come and exactly sit here. But only thing is, loads will be acting in reverse direction. Okay, so loads are acting in this way, and here loads are acting in this way. Similarly, displacements. Here displacements are acting in this way, and displacements are acting reverse direction. So this is anti-symmetry. More example on symmetry and anti-symmetry. So if you take here, this is the perfect symmetry. Loads are acting this fixed beam, simply supported beam, and subjected to UDL, uniform distributed load. Okay, this represents a complete symmetry. If you take half of this model, so the important assumptions is important conditions we need to give is zero slope here. Okay, and zero translation perpendicular to the plane of symmetry. So it is not allowed to move this direction. Coming to anti-symmetry, one side it is we are applying load vertically downwards, other side we are applying load vertically upwards. The displacement pattern looks like this. Okay, when you try to take it as a small symmetry, then the boundary conditions changes here coming compared to here. So here there will be zero displacement. Here we have zero slope. So zero translation in the plane of symmetry. There is no translation in the plane of symmetry. So this is the difference between symmetry and anti-symmetry. And same thing on similarly like reflective symmetry. So when one of a structure is mirror image of other half, then planar or reflective symmetry exists. Okay, it's the same example of symmetry. Structure may look symmetry in shape. If you try to reduce the problem, uh, 1/8 of the geometry there exists a symmetry in 1/8 of a geometry. So you can take this 1/8. If you try to reflect it, it is perfectly we can reflect it. Okay. So this geometry does exhibits 1/8 of a symmetric model. But we also have some condition. It should have symmetry about it should have symmetry in geometry. First is important geometry, and also it should have load symmetry, boundary conditions or displacements. Fourth one, material properties. Okay. So these are the four important things it has to exhibit. Okay. So if you take 1/8 geometry, it is having a geometry symmetry. But what about loads? So is there any loads acting on this side? No. Then 1/8 symmetry doesn't satisfy the load symmetry. Okay. So for that we need to take 1/4 model. So 1/4 model exhibits geometry, loads, displacement and material. Everything it will satisfy. So here the loading is symmetry with respect to horizontal and vertical axis. That means this is vertical and horizontal. Diagonally there is no symmetry for the loads. Whereas geometry exhibits symmetry about horizontal, vertical and diagonal axis. So more example on this example, planar or reflective symmetry. When you take 1/4 model, this is the 1/4 model, symmetry about horizontal and vertical direction, and we need to give boundary conditions for this symmetry. We need to arrest vertical deflection. That means deflection vertically downwards should be arrested. Similarly, horizontal deflection should be arrested at this phase. This will be a quarter symmetry problem where these are the conditions we need to give. Then only it will be represented as plate with hole problem. This problem. So these conditions has to be given at the cut phases. So at this phase, vertical deflection need to be restrained. At this phase, horizontal deflections need to be restrained. Now another example is when load variation is happening along vertical direction, then how it will be symmetry. So here one fourth model if you take, it exists geometric symmetry, material symmetry, but loads it may not. Then we need to take half of this model. So if you take half of this model, when you try to rotate about 360 180 degrees, perfectly it will commence it here, and even loads also same. So here here the conditions we need to restrain this phase horizontally. Okay, it should not move horizontal direction. So if you take 1/4 model, then when you try to rotate about this axis, the loading pattern is not symmetric. So that is the reason we need to take half of the model. Now coming to like I have played with the two materials, material 1 and material 2. Now it is subjected to uniform loading. Now how you will model this one? So here again if you take 1/4 model, loads are symmetric and geometry is symmetric, but materials are not symmetric. So it doesn't satisfy. Then we need to take half of this model, maybe at this location. When you try to reflect about 360 degrees, 180 degrees about this line, it perfectly simulates same complete problem. So this is how we need to take half of this model, and this line is restrained along vertical direction. So these are the conditions we need to give for this model. Similarly, we have repetitive or translational symmetry. So if you take this geometry, so this geometry is repetitive. Okay. So if you model this part, it's sufficient. Okay. Same example, like this is the part. It is subjected to this loading. Okay. Then if you model this part, it is sufficient. No need to model complete thing. So this completes a symmetric modeling, and then comes shell modeling. So in stress analysis, one of the important modeling technique we need to understand is shell modeling. So shell modeling is aggressively used in stress analysis in various locations. So let us see what are the locations. So if you see here in shell model, this is the car. Okay, this car is completely modeled using shell elements. Similarly, this is the parts of aero engine. So these are elements modeled using shell elements. Okay. So shell elements are exclusively used in stress analysis area. Then what is the main usage of these shell elements? Okay. So shell elements are also similar to plane elements. These are also area elements. But in plane elements, like if you take this model, so plate with core loads, we can apply only in plane loads. Okay, but we cannot apply out of plane loads. That means you cannot apply loads acting on the component on the plane. Okay, so in plane loading we can apply in plane stress elements, but out of plane loading we cannot apply. So that's where shell elements have major advantage. And apart from that, these plane stress elements are planar elements. That means this is completely this geometry completely lies in one plane. Okay, that means plane should be this area should be aligned with plane. Okay, whereas shell elements we can go for curved shapes, different shapes we can use it. Okay, so a structure can be approximated as a shell if length to thickness or radius to thickness ratio is 5 or larger. Okay, so you can model a particular component using shell elements if and only if the length to thickness, radius to thickness ratio is 5. Okay, then only 5 or larger, then only we can go for shell elements. So shell elements describes the middle surface of the shell, and the finite element solution represents deformation of the middle surface. Okay, so if you take the below example here, this surface here, we extract mid surface and we'll mesh it shell elements. Okay, and we assign the thickness. So whatever thickness is there, we will assign the thickness to the elements. So when you try to solve this element using the shell elements and solve the analysis, then the results will vary from top to bottom. Okay, so if I take mid surface and do the meshing, then my geometry looks like this. Okay, so when you try to solve this problem using loads, by applying loads and solving it. So for each thing, it will have 3 results: top, middle, and bottom. So it is very important for us to extract results for the top surface, bottom surface, mid surface, and bottom surface. So each element or each node will have three results. Okay, it may be displacement, strain, or stresses, whatever it may be. It will have three results for each location. Shell element allow calculation of membrane bending in plane transfer shear stresses. So that is a major advantage. It will allow the membrane and bending in plane and transfer shear stresses. So typical application of shell elements include thin panels, geometries made with sheet metals. So most of the components like automobile sector, if you take a typical car comprises of a lot of sheet metals. So those things can be modeled using shell elements. So let us take one example of shell modeling. Suppose this is a component we need at various locations, at this location and this location and this location. It looks like this. Then we need to join these two things. So there is a gap exists between this line and this line, and there is a gap exists between this line and this line. So we need to correct it. Okay, we need to join at these points. Similarly, if you take this T joint, if you want to model a shell elements, so it looks like this when you extract mid surface. There exists a gap here. Then we need to correct it. Okay, this is one of the example. So I think one concern is like audio is not coming good. Is it okay or just let me know if you have any concerns about audio? Okay. So this we discussed. So that completes third chapter, model idealization techniques. So just let me know like if you have any questions on this model idealization. So we covered plane stress, plane strain, axisymmetric and cyclic symmetry and various types of symmetries. Otherwise, we'll push to next chapter, finite element modeling. Give me 1 minute. I need to plug in modeling with 1D, 2D, and 3D elements. We'll also discuss about what are the various quality aspects we'll check in the finite element modeling, and also we'll be discussing on mesh convergence, and we'll be talking about the linearity versus non-linearity. What are the various types of non-linearities exist in finite element modeling? This is the chapter 4. So in finite element modeling, before proceeding further, let us understand what is degrees of freedom. Okay, so degrees of freedom typically define what is your problem. Okay, there are various physics involved in finite element modeling that includes structural, thermal, fluid, electric, and magnetic fields. Okay, so degrees of freedom will determine which discipline we are going to work. Okay, so these degrees of freedom determine the position of the mechanism in the space. Okay, so if you take typical this 1D bar, so this it is having a node I and node J. So displacement at node I and node J typically define the position of the of this element. So these are also called as a variables. These nodal variables are assigned to the element as a degrees of freedom of the element. So this is the element. So it has node I, node j, and whatever displacement assigned to I and j node are known as node variables, and these node variables are assigned to the elements. So this is also known as nodal variables, also known as nodal displacements in structures discipline, or in our stress analysis area, it is also called as nodal displacements. So this is a well-known equation for us now, F equals to K into U, where F is a global nodal forces, K is a global stiffness matrix, but U is the known and unknown global nodal degrees of freedom. So on continuing on degrees of freedom, so here we have four different disciplines, and we have put together stiffness matrix, displacement, and force matrix. In elastic or in our stress analysis, K we usually call as stiffness, and U is a displacement, F is a force. In thermal, we'll call it as a conductivity, K as a conductivity, U as a temperature, F as a heat source. In fluid, we'll call it as a viscosity, K we call it as a viscosity, U as a velocity, and F as a body force. In electrostatic, dielectric permittivity is called as a K, electric potential called as a U, and F as a charge. So this is how finite element method is used in various disciplines. So in all these things, primary thing is we'll calculate, we'll solve the finite element equations, complex equations, only to determine U values, which for elastic for stress analysis it is a displacement, for thermal it is temperature, for fluid is velocity, electrostatic is electric potential. And coming to element types, we have various types of element types available. We have a line elements, we have shell elements, we have plane elements, then solid elements, and we have some special elements also. And also we have contact and surface elements. So we it is very important for us to understand what is the linear and what is quadratic. Um, the main on degrees. Okay. Yeah. On element types, we have several types of elements available. Uh, the very basic line types of elements are line elements, plane elements, then shell elements, solid elements that represents the complete 3D, then contact elements, surface elements, and special elements. So these are the various types of elements available in stress analysis. Then coming to type in these elements, there exists one is linear and another one is quadratic. So the basic difference between linear and quadratic is linear is very simple and easy to formulate, and the main drawback is it requires large number of elements to get a solution convergence or to get a accurate results. So to get accurate results with less number, we can use quadratic elements. Okay, so for this is the linear element. If you try to put mid-side nodes at the at, uh, at mid-side locations, then this element is called as a quadratic. Okay, so one of the important aspect of this quadratic is with fewer elements we get accurate results. Let us take a small example on to understand more of linear versus quadratic difference. So this is our actual degrees of freedom distribution. This is node 1 and node 2, or node I, node j, and this is the deformation, actual distribution of deformation or deflection within the element. Okay, so it will vary. It won't vary linearly. It will vary quadratically. Okay, so there exists some curvature in deflection distribution. So when you try to put linear approximation or one element, the distribution is like purely linear, straight line, perfect straight line. Okay. Whereas if you put one element quadratic, the distribution looks, you perfectly capture the actual distribution of the deflection. So same thing, if you try to capture similar results, it requires large number of linear elements to get actual shape. That means instead of one element, we need to put number of elements. So as a simple thing, I have put here only 4 elements, but it may require more than that. So a large number of linear elements are required to get a reasonable and accurate solution. So this is the basic difference between linear and quadratic. Here one element is sufficient to get the results, whereas it requires number of various large number of elements to get the accurate results. Another example between another understanding between linear and quadratic, small example. So if you see here, this is a hollow cylinder. If you see here, so our hollow plate and hollow circular plate. When we put a linear elements, if you see the geometry is not at all captured. Okay. So when I try to put the same number of elements, I did not increase any number of elements, but same number of elements, and I used quadratic elements higher order, then it perfectly captures the geometry. This is the one of the important important difference between linear and quadratic. So quadratic is also used to capture the geometry. The same number of elements, it perfectly captures the geometry. So if you see here, this is the linear and this is the quadratic. So if you see, quadratic elements are curvature. They have curvature here. Okay, whereas they are perfectly straight lines. Linear is perfectly straight line. So same thing it is demonstrated in the tool also. Okay. So coming to linear and quadratic again, we have linear and quadratic in 1D. Okay. So 1D will have three nodes for quadratic and two nodes for linear. For 2D we have various formulations, various forms. One is tria, another is quad. So tria will have three nodes in linear and six nodes in quadratic. In quad we have four node and eight node respectively. Similarly, in 3D, we have various formulations. One is a tria and brick. So, linear tria will have four nodes, and quadratic will have seven nodes. Similarly, in brick, we have eight nodes here and 20 nodes here. Eight nodes in linear and 20 nodes in quadratic. So coming to 3D wedge elements, we have some typos are here, some mistakes are here. Okay. Um, Coming to quad here, brick element, 3D brick element, we have eight noded. So don't see here, these are the typo mistakes are there here. So here we have eight nodes, these are linear, and we have 20 nodes. So eight corner nodes and 12 midside nodes will form as a quadratic. And we have the three, we have three translations at each node. So at each node, we have UX, UI, UZ. It's a 3D problem. We have three translations, 3 degrees of freedom. Similarly, for wedge elements, we have six nodes here, and we have six nodes at corner and nine nodes at mid side. This is a quadratic. This is linear. This is quadratic. So coming to 3D tetrahedron, we usually have like for linear we have four noded, and quadratic we have 10 noded, four at the corner and six at the mid side nodes. But in general, like in stress analysis, people try to put as linear threads. That means four noded threads, which we need to avoid because they are very stiff and they won't give accurate solution. So generally we need to follow, we need to mesh with the quadratic threads if there is a complex shape where we cannot put brick elements. Linear threads need to be avoided. So mixture of bricks and threads are incompatible. Compatibility with mixture of bricks, pyramids and tetrahedron elements. So basically, brick elements will have a rectangle or quad base, and tetrahedron tetrahedron will have tria and quad. So when you try to mesh a component with both the brick and text, so at the interface there is a compatibility issue. One with the quad, one with the tria. So this can be avoided if you use another type of formulation, that is pyramid. Pyramid will have square base and tria faces. Okay. So combination of quad plus tria plus pyramid will have compatibility. So that is a statement here. And coming to pyramid, it will have here also we have three translations. So it is used as an interface for brick elements, and it is available only few softwares. Definitely, it is available in ANSYS, but I am not sure about other softwares. So it will have 5 corner nodes and 8 mid-side nodes. Let us discuss more on this example here. So I have a model here, two components here, two geometries. One I can mesh, both are joined together. Okay, they both are connected. So I can mesh only brick elements here, and I can mesh only tut elements here. So when I try to do the meshing, if you see here all we have um, quad faces. Here we have tria faces, and when they since they are together, then the interface is a completely incompatible. Okay, because they have different types of element faces. Now, if I use a pyramid option, then when I try to mesh it with both brick, tut, and pyramid, then we get a very compatible. If you see, we have like quad faces here, so same quad faces we are getting here, but it is coming through pyramid option. Okay, so all the interface elements are pyramids are found at the interface locations, and this is the these are all TETs. Okay, so when you try to model very complicated geometries, few locations we can go for brick mesh, few locations you cannot go for brick mesh. At that time we need to use this option, we need to use brick plus. No, any questions? I think again audio issue came. So any questions? Maybe I'll stop now because I think past 3 minutes no audio, I think. Okay. So I'll stop for now. I would like to take any questions. Questions, please. or any other software, it will come how it is modeled in, so it will come as is. Okay, so we need to understand which volume is can be sweepable, can be map mesh or sweepable mesh. That volumes we need to chunk it. Okay, we need to do boolean operations such a way that we get a map mesh. So for example, if you see here, so what they have done is, they what they have done is they chunk it here. Like if there are two different colors here, so they chunk it here, and they also chunk it here, and they put a mesh here, swappable mesh here. Similarly, they chunk it here also. So where we can put a very fine, very good, excuse me, very good brick mesh here. So to do this meshing, tet and brick meshing combination, it is very important for us to do Boolean operations on the CAD model available. So I hope that I answered that question. How we separate tets and bricks. I mean how we identify. Okay. How we separate tets and bricks. So it's very easy to identify, right? Tets and bricks. So bricks are all having quad faces. Tets have all trias. Okay. So it is very easy to identify how bricks look like, how tet looks like. Okay. One with square faces, one with the tria faces.